Welcome back. Today we're going to talk about the Stone of Fire, a substance that can literally light up our entire world, or, plunge it into absolute darkness. This is the story of uranium.
Okay, to kick things off, I want you to imagine something really small. Just picture a single ordinary peanut sitting right there in the palm of your hand. Looks pretty small, right? Totally harmless.
All right, now what if that peanut was actually a tiny pellet of uranium? Suddenly, that little thing holds a terrifying, almost magical amount of energy. But, and this is the big but, getting that power out, that's one of the most complicated and dangerous journeys anyone has ever attempted. So let's get into it. How did we even find this hidden fire in a stone?
So this whole incredible story, it doesn't start in some high-tech lab. Nope. It starts with a simple-looking rock that was found centuries ago. And back then, seriously, nobody had a clue about the kind of power that nature had packed inside of it.
For more than 100 years, scientists were just slowly, piece by piece, peeling back the layers of this mystery. I mean, think about it. What was just another metal in 1789 was suddenly found to be shooting out invisible rays by 1896. That discovery blew the doors wide open to radioactivity. But the real game changer, the tiny key that could finally unlock the atom's core, that was the discovery of the neutron in 1932.
And that neutron led them to the ultimate secret, nuclear fission. It sounds complicated, but the idea is actually pretty straightforward. Scientists figured out that if you shoot one of these neutrons at a uranium atom, it splits. And when it splits, it releases a ridiculous amount of energy, way more than any coal or oil could ever dream of. It was like humanity had stumbled upon a whole new, hidden universe of power.
But here's the thing, nature threw a huge wrench in the works. This incredible power wasn't just sitting there for the taking, and it immediately forced humanity to ask a massive question. Are we going to use this to build our world up or to tear it all down? Okay, so this is the challenge I was talking about. When you dig uranium out of the ground, it's mostly made of two different types, or isotopes. As you can see here, more than 99% of it is this stable stuff called uranium-238. The part we actually want, the really energy-packed, fissile version, is U-235. And look at that, it's less than 1% of the total, a tiny, tiny fraction.
So that's the whole ball game right there. If you want to use uranium for anything, whether it's for generating power or, for building a weapon, you have to artificially crank up the percentage of that powerful U-235. And that process, which is incredibly difficult, is called enrichment.
And this chart just lays it out perfectly. It shows you the razor's edge we're walking on. Back in World War II, the Manhattan Project was in a frantic race to enrich uranium all the way up to 90%, and that was to create a weapon of mass destruction. But today, for a nuclear power plant, we only need to enrich it to a really mild 3 to 5%. It's the exact same element, but that one number, the level of enrichment, is the difference between electricity for your home and utter devastation.
All right, so let's get into the nitty-gritty of the process. How does this all actually happen? Well, the journey starts hundreds of feet underground, in some of the most dangerous mines you can possibly imagine. So in places like Canada, they have these incredibly rich uranium deposits, but they're buried under a thick layer of water-soaked sandstone. Mining there is basically a death-defying act. One wrong move, one little crack, and the whole mine could be flooded in an instant. So to get around this, engineers came up with this unbelievable technique. They drill all these holes deep into the ground and pump this super cold liquid through pipes. What does that do? It literally creates a massive, solid wall of ice, a fortress of ice that holds the water back so they can get to the ore safely.
Okay, so once that rock is safely brought up to the surface, its big transformation gets underway. First, it gets crushed into a super fine powder, almost like flour. Then it's mixed with water to create this slurry, which honestly just looks like wet sand. From there, that mixture gets shipped off to a processing plant, where things are about to get a whole lot more dangerous.
And this is where we get to the really high-tech, really dangerous part of the story. This is where science takes that humble powder and turns it into a source of almost unimaginable power.
Okay, so this is where the real physics magic kicks in. That uranium powder gets turned into this super reactive gas, and then it's fed into thousands and thousands of these machines called centrifuges. Now these things spin at just unbelievable speeds, and as they spin, physics takes over. The heavier uranium-238 atoms get flung to the outside wall, while the lighter and much more valuable U-235 atoms start to collect right in the center. It's a painstakingly slow process, but it works.
Once the enrichment is done, that gas is converted back into a powder, which then gets pressed into these small ceramic pellets. And we're back to our peanut. The energy packed into these things is just staggering. A single pellet, about the size of a peanut, holds the same amount of energy as nearly a ton of coal. It's insane.
So these pellets are then carefully stacked, one on top of the other, inside these long tubes made of a special metal called zirconium. These tubes are what we call fuel rods, and then hundreds of these rods are bundled together to create what's called a fuel assembly. This is the heart of a nuclear reactor.
So, inside that reactor, a controlled chain reaction of nuclear fission kicks off, generating an immense amount of heat. That heat boils water, creates steam, the steam spins massive turbines, and boom, you've got electricity for millions of people. It's an incredible process. But this brilliant light has a very, very dark side.
10 years. Just let that sink in. 10 years. That is the minimum time a used fuel rod has to stay submerged in a deep pool of water just to cool down. And that's after being used in a reactor for only 1 year. See, once their useful energy is gone, these fuel rods become one of the most dangerous substances on Earth. They are intensely hot and lethally radioactive. Just being near one would be a death sentence. So they get moved into these deep pools of water for at least a decade, just to cool off. And right now, there are millions of these spent rods sitting in pools just like this, all over the world.
You know, the whole journey of uranium really shows us something profound. Humanity found a key that can unlock an incredible amount of power, enough to light up the entire planet. But with that key comes a heavy and lasting responsibility. We've managed to steal fire from the very heart of the atom, but learning how to control it safely, from the moment it's mined to its final resting place, that might just be our greatest challenge yet.